Have you ever really wondered what's going on inside an AI's brain when it's learning? It can feel like some kind of magic. Well, today we're pulling back the curtain. We're going to break down exactly how these super complex neural networks actually learn, step by step. So let's just start with the biggest question of all, right? What does it even mean for a machine to learn? It's definitely not about just memorizing a bunch of facts. No, it's a way more interesting process, and we're about to unpack it together. And the very first thing to get is that this is absolutely not magic. Not at all. At its core, machine learning is just a really clever and surprisingly simple feedback loop. The whole game is about adjusting millions, sometimes billions, of these little tiny digital knobs inside the network. To really get this, we've got to zoom way in and look at that core feedback loop. You can think of this as the microscopic engine of learning. It's the one process that happens over and over and over again to make the model just a little bit smarter each time. Okay, so that knob I mentioned, it has a technical name. In the world of neural networks, we call it a weight. A weight is really just a number, and it represents how strong a connection is. Now, when a model is brand new, every single one of these weights is set to a completely random value. It basically starts out as a blank slate, knowing absolutely nothing. So, if it starts out knowing nothing, how does it figure out if it's right or wrong? Well, that's where this thing called loss comes in. After the model makes a guess, we calculate its loss. And loss is just a fancy word for a score that tells us exactly how wrong the model was. A really high loss? Terrible guess. A low loss? Hey, it was pretty close. The entire goal of training is to get that loss number as close to zero as humanly possible. And that brings us to the update cycle itself. It's this simple 5-step dance. Step 1, the model predicts. It makes its best guess with the weights it currently has. Step 2, we calculate the loss, just to see how wrong it was. Step 3, we find the direction. Now this is the really clever part. The model figures out for each weight, should I make this number bigger or smaller to lower the loss? Step 4, we calculate the step size, which makes sure we're making a tiny, careful adjustment. And finally, step 5, we update the weight. We just nudge it a little bit in the right direction. This whole loop right here is the heart of learning. Now, that tiny number from step 4, it has a name, the learning rate. And let me tell you, it is absolutely crucial. It controls just how big of an update we make. See, if the learning rate is too big, the model makes these wild, crazy adjustments and it'll never find the right answer. But if it's too small, well, learning would take forever. It's all about taking these small, careful, deliberate steps forward. And when I say small, I mean it. A super common learning rate might look just like this, 0.0001. This basically guarantees that every single adjustment is just a tiny little nudge, which lets the model slowly, incrementally get better without just overshooting the best possible answer. It's the definition of slow and steady wins the race. Okay, so that makes sense for one little weight, right? But a real-world neural network has millions, if not billions of these things. So how on earth does this scale up? Let's zoom back out. The absolute beauty of the system is how well it scales. That 5-step process we just walked through, it doesn't happen for one weight and then the next one and then the one after that. No way. It happens for every single weight in the entire network, all at the same time for every example it sees. Each weight gets its own tiny, unique update, nudging it just a little bit closer to where it needs to be. Now, when the model has gone through every single piece of its training data just one time, we call that an epoch. But learning doesn't just stop after one go-around. The whole process is repeated over and over again, passing that same data through the network many, many times. So here's the key takeaway. With every single epoch, each one of those millions of weights gets just a little bit smarter. They all get tweaked, little by little, to values that, when they all work together, help the model make better and better predictions. And the result? The overall loss goes down, and the model actually gets good at its job. Okay, so that's the theory. It's a really elegant concept, right? But what does this actually look like when a developer sits down to write the code? Let's bridge that gap between the concept and the actual code. And the source material puts it perfectly. It says, let's take a look now at how this training is done with code. This is where we see just how surprisingly simple it is to command this massively complex process. So try to think of the code not as some complicated mess of instructions, but more like a simple control panel. The developer really just needs to set a few key dials, and the framework, the software, handles all of that complicated feedback loop stuff automatically.
The first command is model.compile. This is where you set up the trainer. You choose your optimizer, that's the specific engine for updating the weights, like a popular one called Atom. You set that all-important learning rate we talked about. You tell it which loss formula to use to measure the error. And finally, you give it a list of metrics you want to keep an eye on, like accuracy, so you can watch it learn in real time.
And then comes the magic command, model.fit. This is basically the go button. You just hand it your training data and all the correct answers. You tell it how many examples to look at once, that's the batch size, and how many epochs, or full cycles you want it to run. And with that one single line of code, you kick off that entire massive, multi-million knob feedback loop.
All right, so we've run the code. The training is done. But did it actually work? Did the machine learn anything? Well, the proof, as they say, is in the numbers.
Let's just look at the output here. In the very first epoch, the model was pretty much just guessing, right? It had an accuracy of 55% and a loss of 0.64. But just watch the trend. As the epochs go on, the loss number steadily drops and the accuracy steadily climbs. By the time we hit epoch 20, the loss has been cut by more than half, and the accuracy has jumped to an amazing 93%.
And this chart just tells the whole story, doesn't it? We started with a model that was barely better than a coin flip. And then, 20 cycles of that simple feedback loop later, we have a model that's incredibly accurate. That, right there, is learning in action.
So there you have it. The conclusion is just undeniable. The model learned. That simple, repetitive process of predict, check your error, make a tiny adjustment, when you repeat that millions and millions of times, it allows all those weights to find their sweet spot. The model did exactly what we asked it to do. It minimized its error. It's an unbelievably powerful process, turning a bunch of random numbers into real predictive power. Which leaves us with a final thought to chew on. If this mathematical feedback loop is how a machine learns, what is the one thing it can never truly be taught?